In the last video, we introduced the topic of carbohydrates, of which monosaccharides are the simplest example of carbohydrates. They are the individual sugar units that join together to form carbohydrate molecules. In order to understand and unpack carbohydrates, we need to first understand the chemistry of the individual sugar units. This begins by understanding how to classify some key structural features of these monosaccharide units. Let's take a look in more detail at how we can classify these, and by the end of the video, you should be comfortable with classifying monosaccharides based on the number of carbon atoms in the chain and by the functional group that is present in the carbohydrate molecule. We focus this discussion here on acyclic monosaccharides, monosaccharides where the sugar units are part of a chain rather than part of a ring. In a later video, we will get into chemical reactions where these monosaccharide chains can cyclize to form rings. Let's go ahead and take a closer look at how we go about classifying monosaccharides. So as we take a look at classification of monosaccharides, we're going to break it into two types of classification of these important biomolecules. The first way that we are going to classify monosaccharides is by the number of carbon atoms in the chain. So classify by the number of carbons in the carbon chain that makes up the monosaccharide. When we are referring to monosaccharides, the carbons that are in these chains are not branched chains. Instead, these are just straight linear chains. We get into branching when we look at polysaccharides, molecules that have many sugars joined together. But in the case of monosaccharides are just straight unbranched chains. So we can count directly down the carbon chain and use that as one way of classifying monosaccharides. So when we classify them based on the number of carbon atoms in the chain, we can begin with 3 carbon atoms in the chain. Generally, 3 is the lowest number of carbon atoms that you will find in a monosaccharide, and a 3 carbon atom chain is referred to as a triose. Remember from our last video that the OSE suffix here refers to the fact that this is a carbohydrate. And the tri part of this name is referring to the fact that there's 3 carbons. So the nomenclature here is a little different than what we talked about in our previous organic chemistry, where in our previous organic chemistry unit, 3 carbon atoms was referred to as prop. For example, propane, heating and cooking gas, has 3 carbon atoms. Here we use the term tri to represent 3 carbon atoms in a carbohydrate, a monosaccharide to be specific. 4 carbon atoms in a monosaccharide sugar unit is referred to as a tetrose. With the R referring to 4 carbon atoms, the OSE suffix there referring to the fact that this is a carbohydrate. 5 carbon atoms we refer to as a pentose, with the pent referring to the fact that there are 5 carbon atoms, OSE referring to the fact that this is a carbohydrate. 5 carbon monosaccharides are very, very common, as are 6 carbon monosaccharides, probably the most common because glucose is an example of a so-called hexose, a carbohydrate monosaccharide that has 6 carbon atoms. We can go up higher from there, but these are going to be the common themes that we will see when looking at monosaccharides. So if you are faced with classifying a monosaccharide, one way to do it is to count the number of carbon atoms and refer to it by one of these designations or ways of classifying it based on the number of carbon atoms in the chain. This is not the only way that's valuable to go about classifying a monosaccharide. Monosaccharides are also commonly classified by their functional group, because both the number of carbon atoms in the molecule and the functional group are going to have important implications for determining the final identity of the monosaccharide and also the function that will play biologically. So in classifying monosaccharides by functional group, the distinction between different monosaccharides in terms of functional group is generally whether they have an aldehyde group or a ketone group. Monosaccharides in general will all have hydroxy groups, OH groups, so that's not a good way to distinguish between different monosaccharides, but they do differ in having an aldehyde versus a ketone functional group. And so what we do is we refer to aldoses, where the OSE suffix refers to the fact that it's a carbohydrate, ALD refers to the fact that it has an aldehyde functional group, and if we classify a monosaccharide as an aldose, that's just referring to a monosaccharide that has an aldehyde unit. In contrast, a ketose is referring to a carbohydrate that has a ketone unit present within that monosaccharide structure. Very commonly, when classifying monosaccharides, these two types of classifications, that is, the number of carbon atoms in the chain and the functional group, are joined together to form a single, more complex term that offers a more comprehensive description of the type of molecule that one is dealing with. For example, in this way that these are commonly combined, if we were dealing with a molecule that had an aldehyde functional group and 6 carbons, we would refer to it as an Aldo Hexos. Aldo referring to the fact that it has an aldehyde functional group. Hexose referring to the fact that it has 6 carbon atoms, and those 6 carbon atoms form a typical carbohydrate structure, a molecule that has multiple hydroxy groups along the carbon chain. So we could similarly refer to a kethexose would be a 6 carbon monosaccharide that had a ketone functional group. So we'll commonly see that these three terms, OSE for the carbohydrate at the very end, in the middle there a designation that represents how many carbon atoms are present based on the chart here, and then at the front end of the name, reference to whether there's an aldehyde or ketone functional group there as a more comprehensive way of specifying that a molecule is a monosaccharide, that it has whatever number of carbon atoms it has, and indicating whether it has an aldehyde or a ketone functional group. One way that we could apply this information toward a problem is you might be asked with drawing a specific type of classification of monosaccharide. To apply this information that we've just learned toward an example problem or two, let's take a look at this example. In this example, we are asked to draw a keto-triose. When we are thinking about drawing monosaccharides that fulfill all the criteria of filling in the terminology that goes with this classification, we need to keep 3 things in mind in general to solve this type of problem. So in general, first off, we need to make sure that the molecule has the correct functional group. I'm abbreviating functional group as this FX here. In this particular case, it is a ketone because it's a keto-triose. In other cases, if you saw the term aldo there at the front end of the name, you would know to put an aldehyde group instead. Secondly, keep in mind the number of carbon atoms that the structure must have. In this case, since it says triose, that tells us that the molecule absolutely must have 3 carbon atoms. And then third in the lineup, we need to keep in mind something from the previous video where we introduced carbohydrates and monosaccharides, which was that the general formula of monosaccharides is typically CN, H2N, ON. And the way that we can accomplish that is by placing an OH group on every single carbon atom that isn't part of the ketone or aldehyde group. So to write that out, put an OH on every carbon except the one that is part of the carbonyl group of the aldehyde or ketone. We also need to keep in mind that at those other carbon atoms, we'll always fill the rest of the spaces of the octet by adding hydrogens as needed. we don't get away from the octet rule just because we're dealing with biomolecules. So we still have to follow the octet rule. So let's go ahead and try to draw this keto triose. And I didn't specify here that this has to be a specific type of drawing like a Fissure projection or a line angle formula. So you can draw this out here however you want. I would recommend, since we are referring to it as a triose with 3 carbon atoms, starting by drawing our carbon chain. One of the beautiful things about monosaccharides is that the chains of carbons are going to be just that. They are not going to be branched. So when we say a triose, just draw your 3 carbon atoms in a row, or don't try to put any branches on, in other words. So I drew my 3 carbons in a chain here. The functional group is a ketone, which means that we have to have a carbonyl that is directly bonded to 2 carbon atoms. That is what a ketone is by definition. And so in the case of a keto triose, we only have one possible position where the carbonyl group could go, and that's right here at the middle. If we put it at one of the ends, the molecule would not be a ketone. So I'm going to put the carbonyl group end right here. That allows this to be a ketone. If we had a longer chain molecule, there might be multiple positions where the ketone group could possibly go, and that would be okay. That would create different constitutional isomer sugars, and that does definitely exist in nature. So in this case with a keto triose, there's only one spot where the carbonyl group would go, and other more complex sugars, you might have multiple options of places where you could put the carbonyl group to give different constitutional isomer structures. So now that we've done that, we have, in essence, taken care of criteria 1, getting the functional group in there correctly, criteria 2, getting the number of carbon atoms in there correctly, and then finally, our last order of business here is going to be to fill in the remaining atoms, specifically the OH groups, and adding hydrogens as needed on each carbon to fill the octet rule so that our formula fits this criteria of CnH2nOn. So let's go ahead and do that. I'll start here at the left-hand end of the molecule. Every carbon atom has an OH group unless it has a carbonyl group. So at the very end here, we would have CH2OH needs to be filled in here so that this carbon in blue at the left end of the molecule that I'm highlighting right now has a complete octet. To have a complete octet, it has 1 bond to another carbon, so therefore needs 2 bonds to hydrogen and 1 bond to the hydroxy group to give it 4 bonds in total. The carbonyl group carbon here in the middle already has a complete octet because it has 2 bonds to the carbonyl, 1 bond to the carbon on the right, 1 bond to the carbon on the left, so that one's good to go. And then we come over here to the carbon on the right, and that carbon on the right needs to be CH2OH in order for that carbon that I'm highlighting right here to have a complete octet. It has 1 bond to the carbonyl group, 1 bond to the OH group, and a bond to each of the 2 hydrogen atoms to fill its complete octet. And that will allow us to satisfy criteria number 3 here. So I'm going to go put a check mark on it. And it's always a good idea, rather than just blindly putting a check mark on it like I have here, to actually make sure that we do fulfill that formula. So checking to make sure we fulfill that formula, Cn, N is equal to 3, because we have 3 carbon atoms in blue in this structure. H2N would be 2 times 3. So we should have 6 hydrogens in total here. Let's map those out. We have 1, 2, 3, 4, 5, 6. So that checks out. And then finally, the number of oxygen atoms is equal to the same as what number of carbon atoms we had. So we have 3 carbon atoms, and therefore we should have 3 oxygen atoms as well. And indeed we do. I can verify that by highlighting those in yellow. Oxygen, oxygen, oxygen. So indeed, with that, we can confirm that our formula here matches up with what it was supposed to. So when you are given a classification of a sugar molecule and asked to draw it out, do keep in mind these 3 criteria focus on the functional group, number of carbon atoms, and the general formula CnH2nOn to make sure that you are able to fill that out correctly. Let's do one more example, and we're going to ramp up the intensity a little bit for this particular example problem, in that I am here going to ask you to draw an Aldo Hexos as a Fissure projection. We talked about Fissure projections a couple of videos back. That was in 2 videos prior to now. So if you are feeling a little rusty on Fissure projections, what you should do is take a close look back at video number 354, and that will get you up to speed on that. So here, we're going to follow the same 3 criteria that we did before, focusing on the functional group. The functional group here is going to be an aldehyde because it has the prefix aldo. The number of carbon atoms is going to be 6, and the formula we want to make sure fills the criteria CnH2nOn, and so we can solve that if we have 6 carbon atoms, as has to be the case with a hexose, that there would be 12 hydrogens and 6 oxygens. Now, drawing this as a Fissure projection adds an extra layer of fun to this problem, because remember that a Fissure projection was the type of structure where we drew the carbon atoms in a vertical orientation, starting from the end closer to the aldehyde or ketone group closest to the top, and at each chiral center, we represented each chiral center as a cross of lines here, where the carbon atom that is the chiral center would be what I've put a red dot on, and the rest of the carbon chain would be what flows up and downward here. So our carbon chain is oriented vertically. In our case, we would have 6 carbons in this vertical chain. And then what is to the left and right at these intersections represent the OH and the H at each of those carbon atoms. And the orientation of those will drive what is the stereochemistry of that particular molecule. We'll get into the deeper layers of this and looking at that stereochemistry in more depth a couple of videos down the road from here. So for now, thinking about drawing this as a Fissure projection, I'm going to start by keeping in mind that we're showing this molecule as an aldehyde. So I'm going to put at the top of the chain our aldehyde functional group. I'm drawing the aldehyde group out explicitly as CHO because generally in Fissure projections, it is the chiral centers that we represent as these crosses here. The rest of the molecule we can write out just as a condensed structural formula. So CHO represents our aldehyde group, our standard abbreviation. And then I'm going to come down the chain here and I'm going to put in chiral center here, 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 and here. We'll fill in on down the line right here later. That's going to be our last carbon of the chain. So we have 6 carbons in total. I'm just going to sketch out numbers here to make sure I've done this correctly. 1, 2, 3, 4, 5, and 6. And this also reminds us that each of these intersections represents a carbon. Now we have fulfilled the criteria that we need to, that this is an aldehyde, so I'm going to put a check mark on that. We have 6 carbon atoms, so I'm going to put a check mark on that. And we need to make sure that this fills the formula CnH2nOn. And in order to accomplish that, what we do is we fill in H's as needed at each carbon of the chain, as well as 1 OH group at each of those carbons. And so I'm going to go ahead and fill in those H's and OH's. So I'm going to put OH, H, H, OH, OH, H. I'm just filling in every single one of these carbon atoms of the chain. So it's bonded to an OH and an H. Coming on down the chain to here, H and OH. And then finally at the last carbon of the chain, I'm just going to fill that in as CH2OH because at that position, this particular carbon that I'm highlighting down here at the bottom of the screen would need 2 hydrogens and an OH group to fill its complete octet. And so this will give us a structure that has the formula of C6H12O6. If you were to count up all of those atoms, you would find that this fits. And the way that we took a shortcut to make it fit was we kept in mind that other than the aldehyde group, each and every carbon atom of the chain has a hydroxy group on it, and then however many hydrogens are needed at each position to fill the complete octet. Now, in this molecule has a total of 1, 2, 3, 4 chiral centers. In other words, 4 carbon atoms that have 4 different groups bonded at each of those carbons. And this creates a rather complex stereochemistry situation because each of those individual carbon atoms could exist as the R or S configuration. So there's a huge different number of possible stereoisomers that could exist here because of the fact that at each chiral center there's an option of R or S, RS, 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 and all the different possible combinations. And that is one reason why there are a huge number of different monosaccharides. We will find in nature that naturally occurring sugars take on some specific stereochemistry, meaning some specific RS configurations of these chiral centers. And that is really important because that is one of the key determinants of whether a sugar molecule is perceived by our taste receptors as sweet. It's also one of the key factors that determines how that sugar molecule is metabolized. And in the field of artificial sweeteners, it's been discovered that some stereoisomers of sugars taste sweet but aren't metabolized by the body. And so as a result, they can become 0-calorie sweeteners because they taste sweet to our tongue, but then as they go through the digestive system, the digestive enzymes don't break those down and use them for energy, and hence they do not have calories. They are not processed as typical sugars. So it's a way of sort of tricking our systems into recognizing a molecule as sweet, but yet it doesn't get metabolized like a typical sugar molecule and doesn't have calories. So we will get into more of the implications of the stereochemistry of these molecules in the next video. Stay tuned for that.